student friends and physics loving people. I'm back with another application of time-independent Schrödinger equations. Example number T. In this case we'll discuss about the barrier penetration problem. The first one, the potential step, and in the next video we'll take care of the rectangular potential barrier. Once we understand the potential step problem, it will be easier for us to understand rectangular potential barrier problem. So let's start with the first barrier penetration problem, that's potential step. A potential step is usually defined by this with two regions: one, x less than 0, and where the Vx is 0, potential is 0, and in the region 2 where x is greater than 0, we have Vx equal to V0. And as shown in this figure, this is region number 2 where x is greater than 0. This is the 0 of the x, and on the left hand side of x, this is region number 1. Now coming back to the classical context, we can see that if E is greater than V0, the particle will penetrate the barrier, and with reduced kinetic energy, it will keep moving on the plus x direction. And on the other hand, if E is less than V0, the particle will be reflected because it does not have sufficient energy to cross the barrier. But in quantum context, the situation is something different. If E is greater than V0, the particle may undergo reflection, and for E less than V0, although the transmission coefficient is 0, but the wave function is non-zero. That means there is a finite probability of finding the particle in the second region also. So in terms of a daily life thing, we can understand that if in a normal way, if we have a wall of 5 feet, if you make a jump of 6 feet, definitely will be on the other side of the wall, and if you make a jump of 3 feet, will be on the same side of the wall. This is the normal thing. But if you in the quantum version, even if we make a jump of 3 feet and the wall is 5 feet, the probability is there we may be on the other side of the wall. And also, if even if you are making a jump of 6 feet, we will be on the same side. That means will be get reflected, which from a wall of 5 feet. So this is what happens, or what is made possible by quantum mechanics, which is normally doesn't happen. So let's now construct the Schrödinger equations, and we will consider two cases. First one is E less than V0. So very carefully we construct the time-independent Schrödinger equations with their coefficients alpha square for region 1, and then for region 2 equation 2, where we define the coefficients alpha square equal to this by as given by 3, and then beta square is given by equation 4. We choose these coefficients very carefully, and we see that here alpha square is a positive thing, that means alpha is real, and then beta square, where V0 is greater than E, that means that beta square is positive, making that beta is a real kind of thing. So while constructing time-independent Schrödinger equations, the coefficients to be very carefully chosen so that they remain always real thing, and that's why we are using equation 4, where V0 minus E is taken. If the case is E is greater than V0, in that case we take E minus V0 for these coefficients, which will be clear in the later course of time while discussing the case number 2. And also that the subscripts 1 and 2 simply refers the two regions 1 and 2. And now the solutions are very easy, as we know from our differential equation concept. The first equation has a solution like this: a to the power alpha x plus b to the power minus I alpha x is given by 5. And then the second equation, that means this equation, has a solution like c to the power e beta x plus d to the power minus beta x as given by 6. Now this waves a to the power alpha x, c to the power beta x having plus x are simply waves moving in the plus x direction, and this b to the power minus I alpha x, d to the power minus beta x having minus x here are simply representing waves moving in the minus x direction. Important to note that we may have a wave moving from this side to this side, left to right, but we cannot have a wave moving from right to left because there is no barrier here. Since there is no barrier here, so there will not be any wave that will be moving from right to left. So in that sense, our D will be 0 because this is representing a wave moving from right to left in region 2. So we put D equal to 0, and in that case this equation 6 become equation 7, and equation 7 representing the wave function at the region 2. Now let's use the continuity and boundary conditions for the two wave functions. At x equal to 0, we know that these are the continuity conditions, boundary conditions, u1 is equal to u2, and this gives us a plus b equal to c from equation 5 and 7. And similarly, the continuity condition for the first derivative, that is this condition, would give us from 5 and 7 I alpha a minus b equal to beta c. So solving out all these equations, we find b equal to this as given by equation 8. And now taking the modulus square of this quantity and knowing, as we know all this, how the complex numbers can be simplified, we find that b square, modulus b square, is nothing but it is equal to a square as confirmed by equation 9. These are very simple things that we can do with a simple concepts of complex numbers. Now we can also find a relation between c and a, but we are not interested for timing. Better we are interested in finding the current density. Current density, as we know while finding the equation of continuity, is defined like equation 10, where this RE represents simply the real part of the quantity inside the bracket. So this J will be the definition of current density, and we'll find the current density for different regions. That means corresponding different waves. Now, considering the incident wave as this, because this a e to the power alpha x is simply representing a wave moving from left to right and representing incident wave, and then this b e to the power minus alpha x, which is representing a wave moving from right to left, that means it's representing a reflected wave in the region 1. And then in region 2 we have a wave like c e to the power beta x, which is moving from left to right, that is going from plus x direction. So with all these wave functions or the waves, we can now find out current densities related with every wave here. So incident current density will be given by this incident wave, reflected current density will be given by this reflected wave, and transmitted current density will be given by this wave. So let's first calculate the incident current density from this equation 10. We see that here we put the incident wave function here, or the incident wave, which is a e to the power alpha x, and doing all these things, we find that incident current density is equal to this one, s cross alpha by m modulus a square as given by equation 11. Likewise, we find the reflected current density, where we take the wave as this one. This is the reflected wave, b e to the power minus I alpha x, and doing all these things, we find that reflected current density is as given by 12, which is s cross alpha by m modulus b square. Whereas a negative sign here we neglect, because we are interested in absolute values for current density. And then the transmitted current density, the transmitted wave is this one, c to the power beta x. Doing all these things, we find a quantity like s cross beta by im c modulus square e to the power minus twice, or e to the power minus beta, and e to the power beta cancels out. So s cross beta divided by im c modulus square. Since this quantity does not have a real part, so that means it is equal to 0. Always while calculating the current densities, we are always interested in the real part of the quantity within the bracket, and since that there is no real part here, so this transmitted current density is automatically equal to 0 as given by equation 13. Now let's calculate the reflection and transmission coefficients, which are defined like this: reflected current density by incident current density. And as we see from equation 12 and 11, incident current density and reflected current density, put those values here, and we find that modulus b square by a square, and we know that b square is equal to a square from equation 9, so it is equal to 1. And similarly from equation 13, the transmission coefficient is transmission current density divided by incident current density. Since this part is 0, so definitely transmission coefficient is 0. We also note that this, if we add this r and t, that merely 1 plus 0 equal to 1, so r plus t is equal to 1. Now this important point to be noted always, that if the wave function is a real one, just like this, c to the power beta x, then definitely the current density associated will be 0. So here transmitted current density is 0, because we have a real wave function c to the power beta x in the region 2. So this is how we can calculate these things. The important point is that although t is 0, but the wave function is not 0, because we see that the wave function in the region 2 is given by c to the power beta x. That means that there is a finite probability of finding the particle in the region which is not allowed by classical kind of concept. So this is very important thing, that which we always said in the initial part of the video. Wave function is non-zero, that's why there is a probability of finding a particle, but the transmission coefficient is 0. Also one thing we can put, that we can put B equal to this form in equation 9, and always we remember that if you take modulus of this means that the amplitude of the incident wave, that is A modulus, is always equal to the amplitude of the reflected wave. And only thing is that there is a change of phase on reflection as determined by this phase factor e to the power minus twice IB. Now let's consider the second case. As usual in the region 1, the same equation will be applicable because potential is 0 there, but here potential V naught is less than E. That's why we replace that equation for the region 1, for the region 2, sorry, by this equation as given here. So this is the equation for region 2 in case of E greater than V naught. Now where gamma square is equal to this, as cited earlier, that since E is greater than E is greater than V naught, so this quantity is a positive quantity, and this alpha is gamma square is a positive quantity, and this gamma is a real thing. So while constructing Schrödinger equations, we always have to remember that this coefficients alpha, beta, gamma must always be real, and that's why we have to choose these things like this. And this is confirmed here in equation 16. And the solution of equation 1 already we have done it, is a to the power alpha x plus b to the power minus alpha x, and the solution for region 2 in this case now is given by equation 17, c to the power I gamma x. We see that in the earlier case it was c to the power beta x, now beta is replaced by I gamma in equation 17. So we can now again calculate the incident and reflected current densities, and before that we apply the continuity and boundary conditions here. The quantity condition that x equal to 0 as done earlier is that u1 is equal to u2, and first differentiation of u1 is equal to first differentiation of u2, and so these two conditions would give us a plus b equal to c, and this one I alpha a minus b equal to I gamma c, and simplifying all these things, b equal to this as given by 18 and c equal to this. Now recognizing the incident and reflected waves, we are sure that as seen here that this will be the incident wave as in the earlier case E less than V naught case. In this case also it will be the incident wave, and this b to the power minus alpha x, this is also the reflected wave as in the earlier case E less than V naught. And but the transmitted wave will be different here. The transmitted wave will be now as given by equation 17. So we need not to calculate incident current density and reflected current density because the wave function related with them are same as in the case is less than V naught. So with this transmitted wave c to the power I gamma x, we can now calculate the transmitted current density, which is given like this, and doing all these things we find that transmitted current density is h cross gamma by m c modulus square as given by 20. In the earlier case this transmitted current density was equal to 0 because the wave function was a real one, which was given by c to the power beta x. So comprising of all these things now, and we now see that for this case E greater than V naught, the reflection coefficient is as given usual, this reflected current density by incident current density. Doing all these things we find as given by equation 21. It is alpha minus gamma whole square divided by alpha plus gamma whole square. This is not equal to 0. 21 says that R is not equal to 0. Similarly, T is calculated like ratio between transmitted current density and incident current density, and for using the expression for them we find that it is equal to this, and ultimately it is given by equation 22, 4 alpha gamma divided by alpha plus gamma square, using equation 19 here for the relation between C and A. So with all this already found equations or the relations, we can find the expression for R and T as given by equation 21 and 22. Also we note that if you add up this R and T, you will find that this is equal to 1. So in the earlier case also R plus T equal to 1, and in this case also R plus T also equal to 1. So we see that since, as I stated from equation 21, it's clear that R is not equal to 0. That means that there is a chance of reflection, or we can say that there is a reflection even if the particle has a more energy than the potential state. So for the second case, that E greater than V naught, although the particle has more energy than the barrier, it can be reflected back into the original position or the original region, which is not classically possible or classically thinkable. So lastly we are with some assessment here, that the first one, potential representation, that is Vx equal to 0 for the region 1, Vx equal to V naught for region 2, and a graphical representation. Then how a particle can be present in the classically forbidden region, because the wave function is not 0, non-zero function leads to some probability, but the transmission coefficient is 0 in that case. And then the finding of R and T in terms of those things like transmitted current density, reflected current density, and incident current density, and for a case E greater than V naught. And also our proof that R plus T equal to 1 for E less than V naught, which we have shown throughout this video. So this kind of video can help you certainly understanding the application of Schrödinger equation, and in particular example of potential step will later on will extend to rectangular potential barrier. We'll find that this calculation of R and T will be very helpful in the later course of time also. Thank you very much for watching the video. Keep commenting, and also don't forget to like, subscribe the channel.